Hello everyone, welcome to my course of system programming lectures. This is the first lecture on which I will explain what this course is about, mostly, and then there will be some introductory part, like intro into the world of system programming. Who am I? My name is Vlad. I write code in C and C++ for various backend systems in various fields such as game development, advertisement, databases, and here and there in other fields. And it just so happened that I find system programming very useful in my kind of work, in the backend development, specifically high-load systems and so on. And so eventually I just decided that I want to spread the knowledge I have to more people. And here I am presenting it. The course is consisting of 11 lectures, starting with this one. Each one will be between 2 and 3 hours each. I mean, literally 2 and 3 hours, not academic hours. And in the end, you will get, of some lectures, you will get homeworks, total 5. And one exam, which you can take it yourself or not. I mean, it's YouTube lectures, so I cannot take this exam from you in person, obviously. But I'm also reading these lectures in various universities where I actually take the exam. So link on the slide will lead you to the code examples and homeworks of this course. But otherwise, the lectures themselves are available online by the link you saw on this first slide. So each lecture will be available online. What is this course really? It was created as a part of the educational program of the biggest Russian IT company, VK Group, which used to be called Mail.ru Group. This is where I created it initially in 2018 to be read in Moscow State University to attract talented students for as junior developers into a company, into a database Taran tool, which is being developed right now in VK Group. And then eventually I migrated out of Russia into Germany while I was working at Ubisoft, and where I translated the lectures into English and was delivering them for a while in English as well. And this is the version you will be hearing from me in those videos. What the course will be about. It's system programming on the whole, and Linux especially. And as system programming, I don't mean the development of like electrical engineering stuff and so on. I mean two things actually. Firstly, systematic approach to programming, hence I call it system programming. Secondly, some bits of actual system programming, very low-level development will help you to develop in general backend systems, to understand them better, understand how your code is working, and then you can maybe make wiser decisions when you are coding and designing stuff. So we'll be covering a lot of stuff. It's from the very basic topics, which I think some universities are lacking, not skill, but lacking maybe time to dive into those topics more deep. At least in my experience from what I saw in a few universities, including mine. And we will be covering like real life stuff, starting from virtual memory, file system and devices, processes, multi-threading. We will dive to every single tiny detail from user space down to the hardware. So we will actually see how some transistors are working and how memory is working and disks and so on. And hopefully this will be helpful to you in your like professional, in your career, so to say. The lectures will have a lot of examples, like I do find traditional courses a bit lacking practice, so to say. In my opinion, they're a little bit too theoretical. So in my course, I will be concentrating on more practical and real stuff. So the stuff we will be seeing, I will try to demonstrate on actual examples, which you can also reproduce, compile, and play with them yourself, and so on. Also, the lectures will be having some self-check questions, like on some slides, there will appear a question. You can then hit a pause and try to answer the question yourself based on the knowledge that you heard until that question appeared. Homework tasks I have already mentioned, and the stuff I'm talking right now, you can also read. I find it useful, at least for me, to read stuff, not only to listen. So for those guys who prefer to read, the lectures have a lot of notes online, which you can just read, and they mostly repeat what I'm saying. It's just I will be improvising a little bit more stuff. Some things I will be saying are not yet in the notes, but otherwise, in general, the notes cover pretty much everything I will be saying. And the goal of the course will be that after it's complete, you will actually know how your code is working, down to the kernel, to the transistors, every single system call, what costs how much, what to avoid, how to optimize things, and so on. The lectures are based on mostly on my real life experience, actually. So just some theoretical stuff and things that I didn't work with myself directly, like Linux kernel itself, which we'll also look into briefly, where it will be necessary. I took from books, which you can see on the slide. So Linux kernel development and advanced programming in the Unix environment. There are obviously many more books and many more good books. Among the books probably not mentioned on the slide, I could recommend Operating Systems by Andrew Tannenbaum. I heard it's very good. It's just I didn't read it myself. It's very big, but for those folks who like to read a lot of stuff, heavy books, this will be the one. And this lecture will follow this plan. Firstly, I will explain you what you will need to set up on your PC to be able to do the homework and run the examples if you want. You don't have to. I think those lectures are valuable even if you are not going to actually run the examples or even do the homeworks. Some stuff will still stick in your memory, so hopefully. And then the first lecture being introductory one, it will be light one, so it will not have much tech. I will just introduce you into the world of system programming, where Linux is coming from, various standards, where operating system is coming from, how they work in general, what components they consist of. And it will be a rather short lecture probably, but from the next one we will start with hard stuff, with tech and code. So what will you need in order to be able to do the homeworks and run the examples? Anything which is not Windows. So basically, even if you have Windows, you can still do the things I'm saying. There are at least two options. First would be just install a virtual machine. There is a free virtualization software, VirtualBox, which allows you to literally run inside your Windows and other operating systems like Ubuntu, for example, is the easiest one to run. It will be enough for the course. You can simply follow the installation instructions and get it running, and then you are all set. An alternative solution for Windows would be a VSL, Windows Subsystem for Linux, which for our purpose will be enough, even if you use VSL1. VSL2 is basically virtual machine as well, but VSL1 is also suitable, so install it if you want. Instructions are on the slide, you can also Google it. I will not cover it in too many details. It's all Googleable. So what is really Unix? The name you will be hearing a lot in those lectures. It is a set of operating systems implementing the same programming interface and having similar concepts. And then we call Unix-like. And at the same time, Unix is also a name of a really existing operating system, actually, which was created in 1969 by Dennis Ritchie and Kenneth Thompson in Bell Labs company, which was owned by the company AT&T. And third definition, you could say Unix is a concept, it's an idea to which many operating systems stick. Like how are you supposed to design stuff? How do you represent the objects of your operating system and so on? And also, Unix, last but not least, is a trademark, if you write it in capital letters, of the AT&T company. And now this trademark belongs to the Open Group organization, which is making standards. Worth mentioning that Unix was not created from scratch. It was an evolved version of the commercial operating system called Multics, which in fact is an ancestor of all the operating systems that we have right now. It was developed by the same people who then created Unix. It was introduced in 1964 by MIT, General Electric, and Bell Labs, and despite the operating system was released and was even updated until 90s, so more than 30 years. It is considered to be somewhat a failure, which could surprise you probably. The last working Multics was shut down in 2000 year in the Ministry of Defense of Canada. Just those military guys, they like old stuff. As long as it's working, they will not replace it. And in 1969, Bell Labs abandoned Multics and started Unix. Why Multics is not a success? At least it's not considered success. It was really too ambitious, probably, at least for its time. So, I mean, even if it would become profitable, it probably would not happen soon. And in addition, Multics was too demanding for specific hardware. So now Multics is dead, its source code is published completely in 2011, and in 2014 some fans were able to run it on a simulator of the hardware required for Multics. And it was written in assembly language and PL1, it's programming language 1, the name. However, despite of those failures that we will just mentioned now and we will see a bit more further, Multics introduced some very basic vital features which you can find these days pretty much in every single operating system, and which we treat them like it existed always, but it did not. Somebody invented it at some point, and it happened in Multics. Some examples, like in Multics, the process memory became unified, meaning that you just have process memory and that's it. It could be backed up by the RAM, it could be backed up by disk, could be backed up by whatever else, but there was no longer any separation like this segment of memory belongs to file, this belongs to RAM. So the process where I was able to work with memory, not having to care where this memory is physically stored on. And the address space became segmented. So processes were write into any segment with usual processor instructions, and the operating system will then decide what to do with those updates. Dump them into a file from the main memory and keep it in the main memory. And probably the closest thing you can find to this concept is a system called mmap. It's a function which is invoking a system call in the kernel to extend the memory address space of your process, which you can back up by the main memory or by the disk. So pretty much what was happening in Multics, I guess. And it is available, by the way, the function mmap in C programming language and C++, maybe even in Windows, but I'm not sure. Otherwise, like you can find it pretty much everywhere, except for Windows, maybe even in Windows. Also, Multics introduced dynamic linking. It's an ability of a process to load into its memory not only data, but also executable code. This is how dynamic libraries work, actually, like those files, you know, from Windows DLL or from macdylib dynamic library, or SO files on Linux, which are shared object. And Multics' idea was even more ambitious. They wanted not only to make a process able to load those dynamic files, but even for one process to interact directly with the address space of another process. which sounds to me a little bit like threads. So probably, I mean, we even have this right now, you know, in Linux, you at least in Linux, you can access address space of another process and alter its memory and read it and so on. You need to have special permissions, but it's possible. But I think this idea of making it so easy and accessible doesn't make much sense when you have multi-threading, because this basically does what you need anyway. The original concept was actually never implemented, so perhaps due to poor applicability, as I said. And dynamic libraries these days still exist, and you can load stuff into your process and unload it back, and this is how various plugins are working. The widest application probably is plugins, which you can find quite often in modern development as well. The only perhaps untrivial issue with those dynamic linking these days is that you have to keep in mind that when you load a shared object into your address space of the process, it might be loaded into any position of this address space, right? So in 64-bit systems, your address space is from 0 to 2 in power 64 minus 1. It's a lot of memory. So when you are loading stuff like shared objects, so DLL, dylib, they might end up in any place of this address space, and the code in those shared objects must still work. Which means the code, the machine code in those files must not have any absolute addresses in it. It all must be relative to the beginning of the shared object. And this is why such dynamic libraries you are normally expected to compile with a special flag fpic, which is position independent code. And this is how you create shared objects. Another feature of Multics was runtime changes of the hardware configuration. So at least, I mean, I didn't leave when Multics was existing, so I didn't witness it myself. But from what I know, Multics was supposed to be able to change the hardware. Like you could add or remove CPUs, memory, disks without having to restart the system. And it was one of the first multiprocessor operating systems. To be honest, I can hardly imagine how much applicability this feature has. So probably that's why we don't have it in many places, so to say, these days. Also, in Multics appeared command line interpreter, like what we know these days as bash shell, Z shell, and so on. It was implemented as an ordinary user space program, like we have them right now. Beforehand, a console did not exist as just a user space program. It was kind of a part of the operating system, you could say, or even of the kernel, I guess. And this is when it changed with Multics. So the terminal, the console where you type in your commands, it became a user space program. Probably the remnant of this era when shell was kind of a very embedded part of the operating system you can find in Windows, I think. Because in Windows, the shell cmd.exe, it takes a special place in Windows ecosystem, from what I know. And in Windows, even graphical interfaces, like creating windows and so on, it is also a part of the kernel, from what I know. Also, Multics was positioned as a safe operating system. It introduced the concept of so-called safety rings, which you might hear these days still applied to the modern operating systems. Those are obviously not physical rings, like you don't have rings on the motherboard which are protecting from something. This is a theoretical idea, like you can imagine that every component of the system can be placed on one of those imaginary rings, and each ring has access to certain things, and to access more low-level things, more priority things, it needs to talk to the inner ring. So for example, ring 3 has access to has access, has ability, I don't know, to read user input or something. Ring 2 is able to create new user inputs, or ring 1 then is able to talk to the user inputs of other programs, and ring 0 is able to directly talk with the network and proxy them to user inputs or stuff like that. So each ring provides API to the upper ring. API, I mean, not necessarily like REST API. I mean, it could be a hardware API as well. And then when a system is being designed, different components are placed on different rings and have to use the inner ring to gain access to something more prioritized. In these days, I think rings are basically just two most of the time. It's user space and kernel space. Kernel space can fully control your entire machine, do absolutely everything it wants. User space is pretty much limited in what it can do. It can run some programs which specific user has started, but they will be limited in memory and CPU. They will be able to be put on pause, killed when memory is overused, cannot talk, cannot alter the other programs, and so on. Although in the modern world of virtualization becoming a big trend, and sometimes people say that there are three rings, so ring 0, 1, and -1. And ring -1 would be a hypervisor. So it's a program which runs on your hardware, and on top of which will be running the kernels of different operating systems, which will be sharing one machine. That's how different clouds are working, for example, and VMs in those clouds. Also, Multics introduced a hierarchical file system, which did not exist before. So I hope I should not explain how hierarchical file system is working. You have files, you have folders, they can be nested, that's all. And Multics is a direct ancestor of Unix, so we could probably imagine that Multics was becoming too big, too complex, and then eventually they just forked it, removed unnecessary parts, and created a simplified version called Unix. Even the name, as you can guess, is formed from Multics, where U stands for Unix, uniplexed, and M in Multics stands for multiplexed. And also there is another theory how Unix name appeared from Multics. One of the Bell Lab employees during a demo show, like in some companies even these days, you have demos when team is presenting what they were doing last month, let's say. So during a demo show, proposed the name Unix without X on the end. It would be UNICS. Mocking, then it sounds like Unix meaning castrated Multics. And this is funny, like it's probably an obvious joke for English-speaking people, but if you don't speak, if English is not your native language, try going to Google Translate, for instance, type in Unix as name of the operating system and Unix as the name of those, castrated people, and make it play the sound. Those words sound exactly the same. Although this funny theory was rejected personally by Dennis Ritchie. So probably it's just a joke, or maybe not. Multics ideas listed earlier migrated into Unix for the main part, although in some simplified form, obviously. And all in all, Unix was created as a light operating system, very simple and compact, so it properly worked on the hardware of those old times. And Unix in 1969 was a single task operating system. Even it didn't really have a name back then, it was just created, but they didn't name it yet. It was named a year later, in the year 1970. And probably some of you already spotted a coincidence that this is the year from which we are counting time in computers. Beginning of the epoch, Unix epoch timestamps. They are counted from the midnight 1st January 1970, because this is when Unix appeared actually. But with growing complexity and number of Unix users rising, it became apparent that the operating system needs a manual, it needs versioning, it needs some of those formal processes that an evolving product eventually gets when it's becoming more popular and more used. And eventually in 1971 appeared the documentation for Unix, like manual, which we know these days as the command man. You can use this command, for example, to see documentation for various functions like man read, man write, man socket, man IP, and so on. And you can see documentation for how those functions are working, what they return, what errors they can produce. Not only functions in general, also documentation about networking you can find pretty much detailed in man. C language has appeared in the second version of Unix. Fourth version was already completely rewritten in C in 1973. This was the first version released officially. Before that it was like alpha, beta version, something. And then Unix was evolving and spreading quite swiftly. I mean, C is a simple language, so a lot of people probably were able to read it and alter it and extend and so on, which is much easier than when the system is written in some low-level assembly language or something. And already in 1980s, the 10th version was released, and thousands of people were using Unix. And so far, at that moment, Unix kernel had less than 20,000 lines of C code and a little bit of assembly. So just for comparison, this operating system, entire operating system, was 20,000 lines of code. These days, it's nothing. Like my current project, it has 170,000 lines of code. SQLite has 150,000 lines of code. Tarantul database has 300,000 lines of code. Or let's take like ClickHouse database. It's over 1 million files, not even counting the lines of the code. And the Linux kernel these days has over 1 million lines of code as well. So the growth was quite, since Unix was created, was quite fast, you can say. The thing is that, yeah, Unix was growing popular operating system, gaining success, and it was still owned by a company, which the company AT&T wanted to do to monetize this success, but it was not allowed to make it commercial closed source project because of some anti-monopoly laws in USA, as far as I understand. However, in 1982, AT&T somehow managed to do some shuffling in its sub-companies, and they managed to make Bell System and Bell Labs not a part of the company. I mean, probably they like split the companies and to fight to make it appear like there is no monopoly, and then they closed source the original Unix, and they named it System 5 or System V. To be honest, I don't know how it's correctly pronounced. I think System 5. It is still alive, by the way, System 5. And Oracle Solaris, if you heard about it, is also a descendant of System 5. And after that, it became a problem to use Unix so easily by many people in the world because, especially in the universities, because it was expensive. The System 5 was costing starting from $800 for education, not even for business. It kind of became not so possible to evolve Unix by the community, so to say, and to solve this problem, instead of the original Unix, universities started using a BSD version of Unix, which is called as Berkeley Software Distribution. So that's what BSD stands from. It was forked from Unix in 1977 by the Berkeley University. That's why it's called Berkeley Software Distribution. And systems like FreeBSD, OpenBSD, NetBSD, Darwin were all derived from BSD, and from Darwin were forked systems like Mac OS, iOS, and other Apple systems, by the way. And BSD is memorable not only as an ancestor of some other operating systems like Apple systems. It was actually the first operating system supporting network protocols out of the box. So before that, you can imagine people had to, I guess, write implementation of networking like TCP/UDP manually in user space probably. But in BSD distribution, the networking was available out of the box. You could just install the system and use it right away, the networking. It was in the kernel. And this API these days we call Berkeley sockets, and it became a standard for doing the network API, which is also partially supported even by Windows. So those functions like socket, close, connect, bind, listen, you can find them in Windows as well. And until the end of 80s, Unix systems were geek and student operating systems not suitable for production business, but it was changing. And by the end of 80s, it was spreading into business and government. It's not too hard to deduct that Unix successors were multiplying like rabbits, and everybody could add or fix something and release their own operating system. And at a certain point, it became evident that some sort of standardization is required to make code portable, keep the behavior and APIs the same across many systems. So when you write program for one system, it will also work on another system. And for that, those two different systems has to agree on something, like what each system call is doing, which errors to return and when. Like imagine you have hundreds of different versions of one system, they do different things, the same things differently, and which version will be decided to be the like vanilla one, the standard one, the other versions will have to adopt, change their APIs, change their implementations in order to fit the standard. So whoever is chosen as the standard version will not have to do much, and the others will have to do a lot to catch up with the standard. And the AT&T company started pushing its own standard System 5 interface definition in order to make its version the original one, the standard one, and the others will just have to adopt. And while they do that, Unix like System 5 can be sold in more places, right? And if you have a lot of money, you became surprisingly successful on different activities. Can you imagine, like committees, politics, standards, and so on? And AT&T succeeded. So at that. And at the same time, POSIX standard was published. It's a standard which you might heard about like it's covering, for instance, multi-threading from the most famous pthread library, where some functions, some APIs from the POSIX standard declare how different processes can talk with each other, like named FIFO and so on. We will see more of them during the course. And all those years in 90s, 80s, there appeared united and collapsed a lot of different groups, companies, making standards, and companies were suing each other, arguing with the most correct and original and right Unix. And the AT&T was obviously the most greedy at that. And different standards, it's worth saying, one standard doesn't cover everything. It's like you might have one standard for one kind of API, another standard for another kind of API, another standard for, I don't know, for some protocols, right? So one system will typically contain a lot of different standards for various things and might be conforming with some standards, not conforming with the others. So that they still doesn't exist one standard for everything. And soon after System 5 release, AT&T somehow, I don't know why, they decided to sell their rights, like the trademark, on that operating system to another company. And Dennis Ritchie, back in those days, compared this deal of selling the rights to System 5 with the Bible parable about Esau. According to the legend, he sold his birthright to his twin brother for a mess of pottage. Like imagine your company has the original Unix, the most canonical one, then you just sell it. In the same years, Linus Torvalds finished his version of Unix almost written from scratch. And in 1991, the world saw Linux. Interesting part of Unix history ends here. These days, Unix is more just like a legend. It's not a really used operating system anymore, and its place was taken by Linux. In 2018, Linux kernel had over 23 million lines of code, which means the original Unix, if we count Linux as the successor of Unix, grew more than 1000 times in almost 50 years of evolution. How many products do you know which were living this long? And Linux was not written from scratch though, like some people think. It is based on Unix-like operating system called Minix, created by Andrew Tannenbaum. As a living example of his book, Operating Systems, Design and Implementation, which I have recommended in the beginning of this lecture. It was designed just for education. Like, imagine you write a book about operating systems, then you create an operating system just to show the point how to do operating systems. It's so cool, I mean. And as Linus was saying, he had just wanted to use full power capacity of his new PC and somehow ended up writing a new operating systems kernel. The name, it's obvious, but I will say it anyway. It joins Unix and Linux. That's why it's called Linux. But it was not always so. If you think like Linux created kernel and decided I will name it Linux, it didn't happen so easy, so fast. When Linux was not even released yet, it was just privately used by Linus, he wanted to name it Freaks, from the words free and freak and X from Unix. He even stored the source code in a directory having that name on the university's FTP server. But when he uploaded it there, admin disliked the name. I don't know why. And he renamed it to Linux without asking for permission, and then later Linus just did not object. Maybe he liked the name. But he wanted people to say the name correctly and added an audio record of him saying Linux into the sources of the kernel. It was removed later, but the recording you can still find in other places like YouTube. I think I will just insert a video into this lecture so you can also see it and hear it.
Hello, this is Linus Torvalds and I pronounce Linux as Linux.
In addition, Linus wanted his masterpiece to be free and even invented his own license for that, written in Finnish language. However, in his own words, the operating system consisting only of a kernel is nothing, and like he is right, because kernel will manage the hardware, the processes in the system, scheduling, managing the drivers, file systems, and so on, but it's not enough to run the PC. You still need more things in order for your PC to be usable. You need some sort of console, at least, to be able to type in commands and code. You might also need graphical interface if you're not making stuff for programmers. You need the compiler to be able to compile. You need libraries like standard library to be able to use some features of the language without having to write them from scratch. You might need text editors to be able to code in like whatever environment you prefer, not in the console. And outside of the kernel, you still need somebody to write the drivers, to write the implementation of some file systems. Right? So the kernel is just a small part of the operating system. And Linux, it's just the kernel. It's not the operating system. Coincidentally, at the same time as Linux was emerging another project pursuing the same, like similar goals of the freedom from proprietary code and implementing everything but the kernel. What a coincidence. We know it, this project, probably many of you know it, it's called GNU. Having its own license as well, GNU public license, which is still used. It's getting new versions, but it is still used. And from that time, when those two projects became collaborating, kind of, the Linux kernel became licensed by this license, GNU. What is GNU? This abbreviation doesn't stand for anything. It's a so-called recursive acronym. So GNU is not Unix. It's an acronym which contains itself, and this is an infinite recursion. And this project was set off in 1983 by Richard Stallman from MIT. He was and still is super mad about freedom from corporations and about free and open software and even hardware. You can search his talks on YouTube, like literally just Google Richard Stallman on YouTube. You will find a lot of videos. An interesting person, so to say. From what I heard, he is refusing to use banks, credit cards. His software, everything he uses is open source and free. Even his hardware is produced by some open source, open hardware companies. But this is actually easy to do, right? When you're famous, you have a lot of helpers, assistants who can do those stuff for you when you need it. GNU project, it includes GCC compiler, text editor, Emacs, lots of utilities like ls, grep, make, ld. You probably used at least some of them. Besides, so as to completely dissolve into the free software, never use anything which is not free, and encapsulate the entire ecosystem inside GNU, it was necessary to create a kernel, by means of which it would be possible to develop GNU and be free from the corporations at the same time. And this is now how appeared the kernel GNU Herd in 1990s. Which is alive so far. Although its popularity is far from Linux kernels, which emerged soon after Herd, also using GPL license, GNU public license. My opinion is that Herd would not even appear if Linux would appear a little bit earlier, because Linux pretty much covers the need that GNU project needed. And in 1996, Linux acquired a mascot, the household penguin. He has a history actually. He wasn't just created together with Linux kernel and then being used forever. When Linus wanted to choose a mascot, he mentioned how he was beaten by a small penguin during his visit at the zoo in Australia. And Linus' colleague was inspired by the story and drawn out a first version of the penguin named Tax, an abbreviation from Torvalds Unix. But also tax, like it's again probably obvious for English native people, but for me it was a bit of surprise when I realized that tax is also a costume, which the penguins, they do look like they wear this costume, right? So it's funny. One of the unique Linux kernel's feature is developer community. People from all over the world, from commercial companies, students, to the ones who deem it as a hobby, send their code into the kernel so as to fix something, add a feature, just refactor things, improve something. And some companies specialize in kernel patching and then selling resulting products in a closed source way. So you can take open source Linux, implement something on top of it closed source, and then sell it to businesses and government. And among such companies, there are Dell, IBM, Red Hat, Yandex, VK, I mean Google, obviously, Meta. Pretty much every single big company is doing it these days, and many cloud providers, even who are small, are also patching the kernel in some way or another. And the positive side of this is that for the community, I mean, is that eventually those features implemented by the companies, closed source, they do eventually end up in the open source kernel as well. What would be the motivation for that? Like the company pays for the development time, for the salaries to develop something and then just publish it open source. Well, firstly, they not always publish it right away. It's a common schema that you do something, you sell it for a while, then you publish it after you earn some money. And why publish it at all is that firstly, you gain some reputation in the development world, and your company, I mean, or you as a person, if you are doing it yourself. And secondly, when a feature is being published into the kernel, in a project as big as the kernel, as widely used, you will get a lot of free testing from users of this product, who will be taking the latest version, using your feature, reporting bugs, and other people will come probably and fix those bugs even for you. So you're kind of distributing your development. And at the moment, Linux kernel is used in pretty much most of the backend development, like almost all of it, I guess. And even in many like user-facing places like Android, or in Internet of Things, in TVs, in cameras, and many other devices. And so when Tannenbaum learned that Torvalds created this operating system, he, after a first glance, was displeased by the kernel architecture. The thing is that Tannenbaum deemed microkernel architecture as a superior one, above the monolithic kernel. And there is a well-known phrase of him, Linux is obsolete. He said it a year after Linux's release, and where it is now. This argue was even tiered into 3 sides in the book, Open Sources, Voices from the Open Source Revolution. With a subscription, the world thinks about operating systems design. And it's pretty much Googleable, by the way. There's discussion between Linus and Tannenbaum. You can Google it and find it, as well as many other discussions about open source products, including Linux. It's being held publicly, so you can go and read those things. The thing is that Minix is a microkernel, and Linux is a monolithic kernel. Additionally, like Andrew stated, that Linux is incapable of life because of its lack of portability, which is funny these days, but I guess previously when Linux was just created, it was only working on Linux's PC, perhaps. But nowadays it's obviously not so. Linux can run pretty much on anything. And after all, Linus and Andrew came up to a conclusion that Linux is a great kernel. Its importability is a temporary obstacle as a consequence of not even intending to make it portable. Like making it a point that some product is not portable when it was not even supposed to be portable in the first place. It's a bit strange, but it changed later. Further, I will explain the difference between microkernel and monolithic kernels, so you know what this argument was about. I obviously have a side myself, which I think is the more correct way to do, so I could also argue with somebody. The microkernels appeared as a way to simplify operating systems development, increases durability, so to say, and just parallelize the development. The thing is, when you have a large product as large as a kernel and it's growing, it becomes a very large single piece of software. But it's not a big deal when the product is small, like 20,000 lines of code, 100,000 lines of code, 1 million lines of code. It's still not a huge deal. You can still have it in all in one repository. You can have multiple people working on it in parallel at the same time. But eventually, when product keeps growing, it might become a problem to maintain this huge monolith thing. Sometimes people try to fight it when they split the source code into multiple independent modules, which might be even stored in different repositories, and they would interact with each other, like using networking on some other sort of inter-process communication means. I don't know, they would communicate through one of the modules, which would work as a messaging system for other modules, this kind of stuff. It does indeed improve isolation of the modules, and it becomes easier to understand each of them and develop them in parallel in different teams, maybe even different companies. Also, it is kind of safe, because when one subsystem is down, if you run them in different processes, for example, or even on different machines, like microservice architecture, it will not kill the entire thing. Like your entire system will not die when just one component is dead, which is not so in monolithic kernel or any other single process system. When one module, for example, is crashing, your entire process will crash. It will have to be restarted probably and recover, which might take a while, might be not even possible if something is irreversibly corrupted, and the microkernel supposedly should survive this. The thing is that when you, though, get this microkernel thing, so you have multiple processes running different parts of the kernel, the problem is that, the main problem is that those components will have to interact somehow anyway. Right? And since they are so isolated, they don't share the same address space probably, like multiple threads in one process would do. And so to communicate, they would have to use some EPC means, like communicate through a file, or communicate through networking, local networking, or communicate through some other module which would host a messaging system where one module posts a message and another module reads it and uses it for whatever. It takes a while. This work of unpacking a message, putting it into an APC like message queue, reading it in another process, unpacking it, applying whatever was in this message. It takes a while, it takes CPU time, it takes just time. It takes more memory, so to pack and unpack those things and hold a queue of those messages in the CPC module, it's just slow. So it doesn't scale that well when you need the stuff to be working fast. Those kind of performance issues, I think, were the main reason why microkernels didn't become so widely spread. For instance, Linux is a monolithic kernel, Windows is a monolithic kernel, Mac, like the Apple operating systems, they're also kind of monolithic kernels. You can consider them a little bit of microkernels because some parts of them might be running in multiple processes. For instance, you do have this in, at least in the old versions of the macOS. I don't remember, to be honest, how it is in the recent ones. But you could find, for example, the drivers for Bluetooth, for audio in the list of processes. You can kill them, they will be restarted without having to restart the entire system, which I personally had to use a few times when sound was lagging on my old Mac. Just kill the Bluetooth daemon, it gets restarted, and it's just working again. Yeah, so Apple might be still having this, or at least it used to have it until recently. The Apple operating systems, by the way, they were not created on their own by Apple company just from scratch. They were like descendants of the Darwin operating system, which is a descendant of the Mac operating system, which is descendant of Unix. And you can still see traces of Darwin in and Mac in Apple systems. Like when on Mac, or you type uname command, it will print the name of the system, and it will print Darwin, not Apple, not iOS, not macOS. It will print Darwin still. And I think they cannot even change it anymore because so many tooling depends on uname returning Darwin. And the traces of Mac operating system, you can still find some low-level APIs, how to work with threads, with signals, with exceptions coming from the kernel, I mean, and so on. And the monolithic kernel is different in a way that everything works in one single big process in a single address space, and modules can just communicate with each other by calling functions without having to communicate through some third-party means. This is just working fast. And user space still has to communicate somehow with kernel, like when you are reading input from keyboard. You have to communicate with the kernel because you cannot directly talk to the keyboard from user space process. It's a device. Communication with devices is always through the kernel, so communication with the kernel goes through system calls. We will see how they work in one of the lectures, but for now you just have to know that it's a way to call a function inside the kernel. And the kernel kind of gives you an API of different functions which you can call. And they can do for you various privileged stuff, like accessing the devices if you have the permissions. And this is just working fast. I mean, even the monolithic projects you can organize in a way that they can be developed independently. But having a monolithic kernel allows you to still have them in one address space, then this will be working fast. System calls are not Linux kernel unique feature, by the way. So when I say system calls, a lot of the time I will mean just system calls in general. Every operating system has system calls. If it has user space, it will have system calls. It's just like you can think of modern operating systems of the modern kernels as some sort of runtime for the C language. It's a runtime for C language which gives you like some sort of API in form of C functions which you can call, which are not part of the language but are coming with this runtime thing. Or could also say that kernel like is a library for C. And other languages can access it, but deep down, it always boils down to how C is interacting with the kernel. That's why most of the course we will be using C language, by the way. You cannot get more low level and still has kind of a high level language than with C. And it is also very simple, so even if you don't know C, it should not be a big deal to learn it. Or if you know it a little bit, you will probably already be able to complete the course, I hope. Yeah, it's kind of, there was the same issue and still is as with the as with the public APIs and different standards. Like you do have, for example, C language, C++, they have a standard which compilers have to stick to, and you write program in C or C++ in one system and it supposedly will work in another system the same way. But the system calls, it is still the same problem that different systems do it differently. There is no one standard for system calls for every system. You can see like even the number of system calls is very different in different systems, and they do different things and they behave differently. Sometimes even the same system calls in different systems will do different things. And this is why still to these days you cannot compile program, for example, on Linux and run it on Windows. Unless you were compiling it for Windows on Linux. But if you compile the program to run on Linux, you will not be able to run it on Windows. Unless you use VSL. These days it's kind of a little bit possible. And vice versa. On Windows, if you compiled stuff to run it there, you will not be able to run it on Linux unless you use some special software such as Wine. I don't think this will ever change because different systems have different features and low-level features, and system calls are kind of representing those low-level features. So unless every single operating system in the world will be doing the same stuff, the system calls cannot be standardized. The good news is that system calls are backward compatible inside each system. So if you compile your code for Linux, let's say 3.2.1, then it will run probably also fine on Linux 4.5.6 or something. Right, so programs compiled on for older versions of the kernels will supposedly also run on the new versions of the kernels, but not on different operating systems, at least not so easy. We will see why it is happening again when we will get to the part how the system calls are working on one of the lectures. The stuff above system calls, like which is more high level part of the language perhaps, it is standardized pretty well, I would say. We do have IEEE POSIX standard, which is standardizing a lot of things. We have C standard, C++ standards. Yeah, and there are very, very many different other standards, not so widely known, many of them, like government has its own standards to which your system has to stick in order to be usable in the government structures. And for example, IEEE, it's an Institute of Electrical and Electronics Engineers. They released POSIX in 1988. It is still valid. Most systems stick to it. Mac is conforming, at least partially as well. And most of those standards, like I would even say all of them, they don't define implementations. They define definitions. Like they define behavior, how stuff should be looking, how it should be working, but not how it should be implemented. Because implementation will probably most of the time be system specific. Like you can declare a standard how threads should behave, how they should be created, joined and deleted, how they should run, how can they be interrupted and continued, exited, and so on. But the standard will never say how to implement it, because on Windows it will be implemented in one way, on Mac in another way, on Linux in a third way, on BSD in some other way, and many other systems will do it in their own ways. So, but the implementation details should not matter too much, as long as your program is only relying on what is explicitly stated in the standard and you know that this system is conforming with the standard. Let's summarize this lecture, which is coming to the end. And in the end of each lecture, I will bring up some key points in the end, so you can like try to memorize those things better. And the first point of our summary is that nothing is real Unix except for an old really existing Unix system, which right now is not existing. Linux, macOS, Solaris, BSD, those are slightly different variations of kernels which are Unix-like, but they are not Unix. And kernels we can categorize as monolithic, So they run in one big process normally and micro, which are supposedly consisting of multiple small processes communicating using some sort of inter-process communication means. And there are standards, like for example macOS and Linux follow POSIX standard, at least pthreads support. And following a standard means that the system will provide fixed API with unified expectable behavior, which you can rely on, without having to care how it is implemented. And thank you today for your attention. I hope you liked the lecture, and next time I will present you what the kernel is looking like, what it consists of, what is its structure, and we will see most of the components of the kernel briefly, like what they are supposedly doing, why are they needed, and for some components we will go completely, like cover them entirely and never go back to them again. And for some components we will revisit them in other lectures, and in the end of the next lecture, one of the components we will visit completely is process scheduling. How is it working in Linux at least?